A tyre may look suitable on paper, but its true performance can only be understood when it is tested under realistic terrain conditions. For a military UGV, the tyre must support the vehicle across hard ground, loose soil, sand, mud, slopes, and obstacles. Each terrain places different demands on traction, flotation, durability, stability, and vehicle control. Terrain testing helps engineers verify whether the selected tyre can generate sufficient grip without excessive slipping, sinking, or overheating. It also reveals how the tyre behaves when the vehicle is carrying its maximum payload and operating under demanding field conditions. Without proper testing, a tyre that performs well on a road may fail when exposed to soft soil, sharp obstacles, or repeated high loads. In Part 5 of this training, we will understand how tyres are tested, evaluated, and validated before final selection. Welcome to Part 5 of our tyre technology training, where we will focus on tyre testing. We will begin with load and endurance testing to understand how a tyre performs under repeated loads, operating speeds, and extended running conditions. Second, we will study puncture testing and examine how tyres respond to penetration, cuts, and other forms of physical damage. Third, we will then look at obstacle climb testing to evaluate tyre grip, deformation, and vehicle mobility while crossing steps and difficult obstacles. Fourth, we will explore mud and sand testing to understand traction, wheel slip, flotation and sinkage on soft terrain. Finally, we will examine tyre failure analysis and learn how common failures can be identified and investigated. Together, these topics will help us validate whether a tyre is safe, durable, and suitable for the intended vehicle and mission. This image explains why tyre load testing is essential and introduces the three main types of load tests. Load testing first confirms that the tyre can carry the required vehicle load with an adequate safety margin. It also helps prevent overloaded operating conditions that may cause excessive deformation, overheating, or premature tyre failure. The first method is the static load test, where the load is increased gradually until the target value or failure point is reached. This test measures tyre deflection, deformation, and its ability to support a steady load. The dynamic load test applies repeated cyclic loads to simulate real operating conditions such as impacts, rough terrain, braking, and cornering. Finally, the extreme load test applies loads beyond the rated capacity to identify the tyre's ultimate strength and likely failure mode. Together, these tests help engineers select a tyre that is strong, reliable, and suitable for the vehicle's intended mission. Here we explain the basic tyre load test principle and how the results are interpreted. During the test, a vertical load is applied gradually to the tyre while it rests on a rigid platform. Engineers measure vertical deflection and observe how the tyre's shape deforms as the load increases. The collected load versus deflection data is then plotted as a curve. The design load represents the normal operating load, while the maximum load indicates the tyre's rated capacity. The relationship between ultimate load and design load provides the tyre's safety factor. This helps engineers confirm that the tyre has sufficient strength and operating margin for the intended vehicle. Here we show the 6 basic steps of a static tyre load test. First, the tyre is mounted on the specified rim, inflated to the test pressure and installed in the vertical load frame. A small preload is applied, the instruments are zeroed, and the load is then increased in controlled steps. At every stage, engineers record load, deflection, strain, and visible deformation. Testing continues until the target load, excessive deflection, or failure is reached. The equipment typically includes a hydraulic actuator, load cell, load platen, base plate, and data acquisition system. Here we explain how a dynamic load test evaluates a tyre under repeated operating loads. A hydraulic actuator applies cyclic vertical forces through the load platen, repeatedly compressing and releasing the tyre. The test conditions are controlled using inputs such as load amplitude, frequency, temperature, and duration. During testing, engineers monitor deflection, heat buildup, deformation, and the beginning of cracks. These repeated cycles simulate braking, cornering, rough terrain, vibration, and obstacle impacts. The results show whether the tyre meets its endurance target or develops excessive heat, structural damage, or fatigue failure. Let us understand why endurance testing is essential for verifying a tyre's long-term durability and reliability. It reveals wear, heat buildup, and structural degradation that may develop during extended operation. Endurance testing also confirms the expected service life and reduces the risk of tyre failure during a mission. During the test, the tyre operates continuously under controlled load, speed, and inflation pressure. The test continues until a specified time or distance target is achieved. Engineers continuously monitor, measure, analyze, and evaluate the tyre's condition throughout the test. Ultimately, better endurance supports greater reliability and improved mission success. Here we show a typical tyre endurance test setup used to simulate continuous real-world rolling conditions. The tyre and rim assembly is mounted against a rotating drum while a controlled vertical load is applied. A pressure control system maintains the required inflation pressure, while sensors and a data acquisition system monitor tyre performance. In this example, the tyre carries 4,000 kilograms at 450 kilopascals and runs at 50 kilometers per hour. The test continues for about 5,000 kilometers or approximately 100 hours under controlled temperature conditions. The tyre passes when it completes the test without structural failure and remains within the required performance limits. Here we highlight the key parameters monitored throughout a tyre endurance test. Engineers track tread and sidewall temperature, inflation pressure, and tyre deflection to confirm stable operation under load. Vibration is also monitored because increasing levels may indicate imbalance, belt separation, or structural damage. Tread depth is measured at regular distance intervals to calculate the rate of wear. Visual inspections identify cuts, cracks, bulges, sidewall damage, and tread chunking before they become critical failures. Endurance testing combines controlled laboratory drum tests with real-world road trials for reliable validation. We have now completed load and endurance testing and understood how tyres are evaluated under repeated loads, speeds, and operating cycles. Let us now move to puncture testing, where we will examine how a tyre responds to penetration, cuts, and other forms of physical damage. This testing helps determine whether the tyre can continue supporting the vehicle safely after sustaining damage. This image explains why puncture testing is important for tyres operating in demanding environments. It simulates real-world threats such as nails, spikes, sharp debris, and shrapnel. The test verifies air retention, slow leak behavior, and the tyre's ability to continue operating after damage. Common methods include nail or spike penetration, sharp object penetration, and high-energy debris impact testing. These tests help engineers evaluate puncture resistance, run-flat capability, and the risk of vehicle immobilization. For military vehicles, continued mobility after a puncture can directly support safety and mission success. Here we explain the basic puncture test process and the different objects used to damage the tyre in a controlled manner. The test begins by penetrating the tread with a selected object under defined conditions. Engineers then measure the immediate air loss, calculate the leak rate, and evaluate whether the vehicle can continue moving in a run-flat condition. Typical puncture objects include nails, steel spikes, sharp chisels, and cone-tipped penetrators. High-velocity ballistic debris may also be used to simulate fragment or shrapnel impact. Together, these tests determine puncture resistance, air retention, and the tire's ability to support continued mission mobility. Let us see how a typical puncture test procedure works. In Step 1, the tire is prepared by setting it to the specified inflation pressure and test condition. In Step 2, the test object, such as a nail or spike, is positioned carefully so it is aligned with the center of the tread. In Step 3, the object is driven into the tire at a defined speed and force to create a controlled puncture. Steps 4 and 5 then focus on recording the initial air pressure drop and monitoring how the pressure continues to decay over time. Finally, in Step 6, a mobility or run-flat test may be performed to see whether the vehicle can still move and how its performance is affected after puncture. This table presents an example puncture test results for different test objects used to evaluate tire damage tolerance and continued mobility. Each row compares a specific object including a nail, spike, chisel, cone tip, and ballistic debris, along with its size. The next columns show the initial air loss after puncture, the leak rate over time, and the run-flat distance the tire was able to achieve. We can see that the chisel creates the highest initial air loss and leak rate, while the nail produces the lowest values in this example. Even with these different puncture conditions, all test cases still achieved significant run-flat distance between 55 and 70 kilometers. The final result column shows a pass for every case, indicating that the tire met the required puncture and mobility performance criteria. We have now completed puncture testing and understood how tires are evaluated against penetration, cuts, and physical damage. Let us now move to obstacle climb testing, where we will study how the tire and vehicle behave while crossing steps and difficult obstacles. This test helps evaluate tire grip, deformation, stability, and overall obstacle crossing capability. Let us understand the purpose of obstacle climb testing and the common obstacle types used to evaluate military vehicle tires. The test verifies whether the tire can climb vertical or near-vertical obstacles while maintaining traction, control deformation, and structural integrity. It also checks rim protection and confirms that the vehicle can negotiate difficult terrain without becoming immobilized. The examples on the right include step climbs, irregular rocks, urban curbs, logs or pipes, and ramp breakovers. Each obstacle introduces a different challenge through its height, diameter, shape, or approach angle. Together, these tests show whether the tire can support reliable obstacle negotiation, vehicle mobility, and mission success. Let us understand the typical obstacle climb test setup and the key measurements used to evaluate tire performance. On the left, the test wheel approaches a step obstacle with the suspension at right height and a controlled approach angle. The center panel defines the test conditions, including inflation pressure, rated vehicle load, speed, surface type, and operating environment. On the right, engineers measure obstacle height, approach and departure angles, climb success, tire deformation, and wheel slip. They also inspect for cuts, bruises, or bead unseating while monitoring vehicle pitch, roll, and lateral stability. Together, these measurements confirm whether the tire can climb the obstacle safely without losing traction or structural integrity. Let us understand the example performance targets used to evaluate obstacle climbing capability across different vehicle classes. The table compares light UGVs, tactical UGVs, heavy UGVs, and smaller robotic platforms using step height, approach angle, success rate, and damage limits. As vehicle size increases, the expected obstacle height and approach angle generally increase as well. All vehicle classes are expected to achieve at least a 95% success rate with no tyre failures. The pass criteria require the tyre to climb without loss of mobility, bead unseating, structural damage, or excessive air loss. The vehicle must also remain stable throughout both the climb and descent. We have now completed obstacle climb testing and understood how tyres influence the vehicle's ability to cross difficult obstacles. Let us now move to mud and sand testing, where tyre performance is evaluated on loose and soft terrain. These tests help us understand traction, flotation, wheel slip, sinkage, and the risk of the vehicle becoming immobilized. Let us understand the purpose of mud testing and the different mud conditions used to evaluate tyre mobility. The test measures traction, sinkage, wheel slip, and forward progress while also checking whether the tread can clean itself effectively. On the right, mud conditions are grouped as light, medium, deep, and extreme, mainly according to depth, softness, and water content. As the mud becomes deeper and wetter, rolling resistance and the risk of vehicle immobilization increase. Testing across these conditions helps engineers confirm that the tyre can maintain traction, flotation, and reliable mobility in realistic operational environments. Effective mud mobility depends on the combined performance of traction, tread self-cleaning, and flotation. Let us understand the key measurements used in mud testing and how each one is obtained. The first two measurements are sinkage, which shows how deeply the wheel penetrates the mud, and wheel slip, which compares wheel speed with actual ground speed. Next, tractive force measures the pulling force generated at the tyre, while progress rate shows how quickly the vehicle moves forward through the mud. The slide also tracks temperature to monitor heat at the tyre and hub, and self-cleaning to assess how well mud is expelled from the tread voids. Each parameter is linked to a practical measurement method, such as rules or lasers, wheel speed sensors, DGPS, load cells, IR cameras, or visual rating after the run. Together, these measurements help engineers evaluate traction, mobility, thermal behavior, and tread effectiveness in challenging mud conditions. Let us understand the example mud test results and how tyre performance changes as the terrain becomes more severe. The table compares 4 runs across light, medium, deep, and extreme mud conditions. As mud depth increases, tyre sinkage and wheel slip also rise, while the vehicle's forward progress steadily decreases. The self-cleaning rating also drops from 4 in light and medium mud to only 2 in extreme mud. The tyre passes the first 3 runs but fails in extreme mud because the overall performance falls below the required target. This example shows why every test result must meet the defined limits before the tyre can be accepted for mission use. Let us understand the purpose of sand testing and the different sand conditions used to evaluate tyre mobility. The test checks flotation, traction and self-propulsion while measuring sinkage, wheel slip and forward progress. It also helps engineers compare tyre designs, tread patterns and inflation pressures for desert operations. On the right, the sand types progress from firm sand to loose sand, soft sand and dune sand. As the sand becomes finer and less supportive, rolling resistance and the risk of excessive sinkage increase. Reliable sand mobility therefore depends on strong traction, good flotation, and low sinkage across representative operational terrain. Let us understand the sand test principle and the typical setup used to evaluate tyre and vehicle mobility. The vehicle enters the sand section at a controlled speed and travels a specified distance while load, tyre pressure and speed remain constant. During the run, engineers measure sinkage, wheel slip, temperature, speed and forward progress, then compare the results with defined performance targets. The test track includes an entry zone for stabilization, a central test section for constant speed measurement, and an exit zone for recovery. Test conditions define inflation pressure, vehicle load, speed, sand depth, distance, environment, and the number of repeated runs. Together, these measurements show whether the tyre can maintain traction, flotation, and reliable mobility across sandy terrain. Let us understand the example sand test results and how tyre performance changes as the terrain becomes deeper and softer. The table compares 5 runs across firm, loose, soft, and dune sand conditions. As sand depth increases, sinkage and wheel slip rise, while the vehicle's forward progress steadily decreases. The self-cleaning rating also drops from 4 in firm and loose sand to 2 in the deeper dune conditions. The tyre passes the first 3 runs, but fails in both dune sand tests because mobility performance falls below the required target. This shows why every result must meet or exceed the defined limits before the tyre can be accepted for mission use. We have now completed mud and sand testing and understood how tyres perform on loose, soft, and low-bearing capacity terrain. Let us now move to tyre failure analysis, where we will examine the common ways in which a tyre can become damaged or fail. Understanding these failure modes helps engineers identify root causes and improve tyre selection, operation, and maintenance. Let us understand some major tyre failure modes and the visual signs that help engineers identify their likely causes. The first is sidewall failure, where cuts, punctures, fatigue, or excessive flexing damage the tyre's outer wall. Typical signs include cracks, tears, bulges, blisters, and exposed fabric or reinforcing cords. Common causes are sharp debris, underinflation, overloading, and impact damage during side slope or obstacle operation. The second is bead failure at the tyre-to-rim interface, which may cause the bead to deform, break, or become unseated. It often appears as a torn bead, air leakage, or partial separation of the tyre from the rim. Likely causes include low pressure, obstacle impacts, high side loads, and an incorrect or damaged rim. The third is belt separation, where the internal steel belts separate from the surrounding rubber. This may produce bulges, distorted tread, vibration, and uneven wear, and can lead to sudden, catastrophic failure. Overheating, high-speed operation under heavy load, impact damage, and manufacturing defects are common root causes. Recognizing these symptoms early helps engineers identify the failure mechanism, correct the operating condition, and prevent repeated mission failures. Let us understand 2 more tyre failure modes: overheating and tread chunking. Overheating occurs when excessive internal temperature builds up and begins to degrade the rubber and internal tyre components. Typical warning signs include hot sidewalls, rubber discoloration, a soft or sticky tread surface, and unusually rapid wear. The most common causes are underinflation, overloading, high-speed operation, and high ambient temperature. Tread chunking is the loss of pieces of tread rubber caused by severe stress, impacts, or excessive heat. It appears as missing tread blocks, an irregular tread surface, increased road noise, and reduced traction. Common root causes include sharp or rocky terrain, high torque during rapid acceleration, an unsuitable tread compound, and overheating. Both failure modes reduce tyre reliability and may quickly affect vehicle mobility if they are not detected early. Regular inspection, correct inflation pressure, suitable loading, and controlled operating speed are therefore essential for prevention. This concludes Part 5 of our tyre technology training, where we focused on tyre testing. We began with load and endurance testing, then explored puncture testing and examined how tyres respond to penetration, cuts, and physical damage. Next, we studied obstacle climb testing followed by mud and sand testing, focusing on traction, wheel slip, and sinkage on soft terrain. Finally, we examined tire failure analysis. Thank you for attending the tire technology training sessions. We hope you enjoyed the program and now have a stronger understanding of tire selection, integration, and testing.